Okay. Good afternoon. So my name is Toni Pasanen, and I work as a senior project engineer in a company called ELFys, and I'm also one of the co-founders of the company. In this presentation, I will tell you about our high-sensitivity photodiode products, focusing especially on their application in the spectroscopy and sensing field. I have structured my presentation as follows. So first, we will have a quick look on the background of ELFys. We'll then focus on our patented black silicon induced junction technology and what kind of superior photodiode performance it provides. We will then move on to a few selected application examples where I will show you what kind of benefits one can get from our technology in a few case examples. And finally, I will show you some highlights from our product development pipeline and what you can expect from us in the near future. Let's start with a few words about us. So ELFys is founded in 2017 based on long-term research work on photodiode technologies done in the Aalto University in Finland. We have currently 15 full-time employees. Half of us have a Doctor of Science degree, which is highlighting our focus on the high performance and the deep technology that we apply in our photodiodes. We have already more than 70 customers in 17 countries, and we have quite nice distributor network covering the main business areas in the field. Around 2 years ago, we raised 6 million euros for scaling up our production. The investors include, for instance, Samsung and the founders of the Aura smart ring. Today, we have our semi-mass scale production up and running at the Micronova Nanofabrication Center in Finland, where we also do our research and development. And we recently announced a big milestone for us that we have delivered the first samples from a mass production foundry where we are ramping up our production to a really high volume scale needed, for instance, in some consumer applications. If you then move on to the actual technology, what you see here is the so-called black silicon nanostructure that we use in our photodetectors. So the dimensions of these silicon spikes have been carefully optimized so that, to use simple terms, the light that enters this kind of spikes, woods of silicon spikes, doesn't find its way out, but it gets lost here and it gets absorbed. In more scientific terms, here is a graded refractive index from air to silicon, and since there is no interface, no light is reflected, and we absorbed all the photons that arrive to the photodiode surface. We use also another nanotechnology method in our photodiodes called atomic layer deposition that we use to coat the surface with a highly charged thin film, by which we create a so-called induced junction at the surface that we can use to highly efficiently collect all the electrons and holes, all the charge carriers generated by the absorbed photons. Putting these two nanotechnologies together, we get what we call a black silicon induced junction photodiode, which is the invention we made back in the days in the university, patented it, and afterwards we have now successfully commercialized it at ELFys. Let's then look at the performance that we have in our photodiodes. So I will show you on this slide the photoresponse of the photodiode products as a function of the wavelength. With blue, you see the data from our photodiode, and then with the dashed line, I have highlighted here the ideal performance for a photodiode, meaning that the external quantum efficiency is 100%. And in this case, every single photon that arrives to the diode surface is absorbed, and every single charge carrier that is generated is collected. So that means EQE of 100%. And as you see, the response of our photodiodes follows very clearly, very closely at the ideal limit. So we can literally capture every single ray of light that arrives to the photodiode surface. This data, it's not only measured by us, it has also been certified independently by world-class metrology institutes, including the Physikalisch-Technische Bundesanstalt here in Germany, the Brookhaven National Laboratory in the United States, and also the Finnish Metrology Institute at VTT. Let's look at the data in a little bit different format. So I show you now the external quantum efficiency of the photodiodes as a function of the wavelength, and again with dashed line I highlight the ideal performance for a photodiode, 100% EQE. Here you first see the data taken from two big players in the field, from conventional technologies, photodiodes based on conventional technologies. The one is called UV enhanced photodiode, and the other one is IR enhanced by the manufacturer. And as you see, it is well possible to reach quite high performance in the wavelength range where the photodiode is optimized for. But then if you go away from this optimum wavelength, the performance starts to quickly drop, and actually this anti-reflection technology that is normally used in the conventional photodiodes may even worsen the performance for the other wavelengths than what is the optimum wavelength. This is not the case for our black silicon photodiodes, so we have more than 96% external quantum efficiency for the whole wavelength range visible here, and that is relevant for the silicon-based photodiode. And actually for most of the wavelengths, the quantum efficiency is more than 99%. Let's have a little bit closer look on the photoresponse and focus on the different wavelength regimes. If we start from the UV, we can see that at 200 nanometers we have as high as more than 0.2 amperes per watt responsivity, which is several times higher than in any of the competing devices. The external quantum efficiency actually even exceeds 100% for the very short wavelength range shown here. That is not a measurement error, but it is because of the phenomenon called impact ionization. So the photons in this region have that high energy that they can generate more than one electron and hole per photon, and with our technology we can collect all of them. In the visible wavelength region, our performance follows very closely the ideal performance, more than 99% external quantum efficiency. At near infrared, the maximum responsivity is 0.75, obtained at 960 nanometers. After that, the performance or the photoresponse naturally starts to drop because it's a silicon-based device. The silicon material starts to become more and more transparent, but still at 1.1 micron wavelength, we have more than 60% EQE, which is quite exceptional for a silicon-based photodiode. Yet another interesting property of the black silicon surface is that the reflection from the surface remains very close to zero also when the light is coming from a large angle. So you see here the reflectance spectrum measured at different incidence angles, and you see that up to 60 degrees angle the reflection is basically zero, and then at 70 degrees angle it's still only 10%. And this directly translates to very large sensing angle of the device. So at 70 degrees incident angle, the EQE is still around 90%. This kind of high performance naturally finds benefits in numerous different applications, and actually our technology provides potential to improve the performance of the final application in any application where light needs to be measured. I have highlighted some examples here, and on the following slides we will go in more detail in a few selected examples. Let's start from spectroscopy. So in this kind of spectroscopy instruments, the user normally wants to measure the spectrum that is reflected or transmitted or emitted from the sample, and then from the measured spectra and the spikes or different features in the spectra, one can obtain information about, for instance, what kind of substances there are in the sample or what kind of bonds there are between the different atoms or molecules. And for this application, our technology provides benefits in a few different ways. First of all, since the sensitivity is very high and the noise is at the same time very low, as is typical for a silicon-based diode, the signal-to-noise ratio is very high, and that provides potential to even for the user to see finer structures in the spectra. So you can detect finer structures in the spectra and then get more information from the sample and possibly measure smaller concentrations in the substances. With conventional diodes, if the noise level is higher compared to the signal level, it may be that you don't observe those spikes, but they are lost in the noise level. Of course, the wide detection angle also increases the signal level, but this also provides a benefit in a different way that if we have a normal or conventional photodiode, the surface is normally reflecting some light. And then some part of the light that is coming to the diode surface reflects back to the interior parts of the spectroscopy instrument. And then again, there are most likely some parts inside the device where the light reflects back to the photodiode. And that is then causing some false signal in the measurement. But with our diodes, that is not a problem because our diodes, they have a very nice matte black surface with no reflection. So that makes it simpler for the designers of the spectroscopy instruments. You don't need to take this back reflection into account. And a third benefit is, of course, the very wide band performance, starting from the UV through the visible to the near infrared. So using conventional diodes, if the user of the final device wants to measure samples, let's say that one sample is emitting UV light, the other sample is emitting near infrared light, you would need to input 2 photodiodes optimized for these different wavelength range in the instrument. But with our diode, you can cover the whole range with just a single photodiode. We have quite many satisfied customers in this field. One reference that we can mention is Tool Labs. They have recently launched Redstone Fourier transparent optical spectrum analyzer, and they are using our photodiodes in this product. So we have got quite nice feedback from this, as their R&D manager states that with our innovative photodiode technology, they have managed to boost the device performance with respect to the wavelength range, lowering the noise, increasing the resolution, and also the sensitivity, which are all, of course, highly important for this kind of spectroscopy instruments. We have also been running projects for the European Space Agency, and as part of those projects, the stability of our devices and technology has been tested against quite tough requirements set by the ESA. And our technology and products have proven to even exceed those requirements with respect to the quite harsh humid conditions, also different temperatures. So basically the photodiodes have been in a sauna, and also different radiation sources. Another example that I have picked here is X-ray detection. It could also be any other highly energetic photon detection. In this case, we have here a scintillator material that is absorbing the X-rays, and then the scintillator is emitting light that is typical for this scintillator material in use. And since the light emission takes place in all directions from the scintillator, the property of our black silicon technology to absorb the light that comes also from a very wide angle is highly beneficial. And our technology has been tested against conventional photodiode. Here I show you the normalized current measured from the photodiode for a different X-ray tube voltages, and as you see, our photodiodes provide 30 to 50% higher signal depending on what kind of X-ray voltage is used. So this same trend also agrees for visible light. So normally in the low light conditions especially, you get the highest benefit from our technology, since the signal to noise ratio is greatly enhanced. A third example is wearable health monitoring, which I think is quite an everyday application for many of us, having some smartwatches or smart rings in your hands. So in these kind of devices, normally green and red LEDs are used on the backside of the watch or ring or some other device, and they are shining the light against your skin, and then the reflected or transmitted light is measured with the photodiode. And then from the photodiode electrical signal, using some smart algorithms, one can, for instance, measure your heart rate or blood oxygen level or different parameters. Here I will show you the external quantum efficiency for our diode. In this case, the yellow curve here, our photodiode is now packaged in a so-called surface mount type of package, so it's molded in optical epoxy to give it more mechanical stability, because the photodiode is meant to be pressed against your skin. So of course it needs to be highly mechanically durable. And then for reference, we have here with the purple some other state-of-the-art technology that is actually a model that is quite commonly today used in this kind of wearable applications. And as you see, our photodiode provides 50% higher performance for the green wavelength and 15% higher performance for the red wavelengths. And of course, this then provides quite big improvements for the device performance. So first of all, since the signal levels are higher, one can use that as a benefit to improve the accuracy of the measurement data. Another way is that since you can see you have higher quality data from the photodiode, the designers of the wearable devices can possibly measure some new parameters from the body based on the new improved sensitivity, and that of course then increases or improves the sales in this highly competed market if they can implement some new features in their devices. Another way of benefiting from our technology is that if you are happy with the current signal level that you are coming from the photodiode, you can actually run the LEDs with smaller power and still get the same signal level because our photodiode is producing the higher current, and that then translates into extended battery life in the best case. A third way, again, if you are satisfied with the current signal level, you can reduce the size of the photodiode and still get the same signal level, and that then helps to trying to make smaller devices, as is typically the trend, and also it gives more freedom for the optical designers of these measurement instruments. We have recently published a white paper about this topic, so if you are interested to learn more about the application of our photodiodes in the wearable health monitoring applications, please check our web pages. You can download it from there, or of course just directly reach me and I will share it with you. We are currently involved in a project in this field called PhotonWear, where we are with quite big players in the field developing new advanced wearable devices and also technologies, not only for the consumer products but also for the different medical applications. Here you will see a snippet from our standard product catalog. So we have divided our standard photodiodes in two different product lines. One of them is the so-called SM or surface mount type of products. They are mainly meant for the wearable health monitoring applications. Some images shown here. So they are packaged in the optical epoxy and molded there for the best mechanical stability. Oops. And then the other product line is the so-called PD product line, where we have collected the most frequently requested photodiode types as our standard products that are available from the shelf. The dimensions of the photosensitive area or the size ranges from 1 to 100 square millimeters. Also, we have different packaging options available, starting from the standard TO cans, different ceramical substrates, also different printed circuit boards are possible. But we are also highly flexible in doing customized solutions for the customer needs. So please reach us out if you have if you got interested, so that we can discuss together how you would get the most out of our technology to boost your device performance. We have also done some arrays or small matrices. Let's then have a look on some selected highlights from our product development pipeline. The first one is CMOS image sensors. So even though the CMOS technology is highly advanced today, it's still rather challenging to get high quality images with the cameras in low light conditions, since the noise level is limiting the signal. And we think that in this field we would have something to give and to improve the performance of the device. And we are actually collaborating at the moment and working with a few manufacturers in this field to implementing our technology in their existing CMOS sensors. I have some preliminary prototype data here where the black silicon technology has been applied in commercial CMOS sensors. So the only difference between these two CMOS sensors here is that the black silicon technology has been implemented on one, and then the other one is the commercial sensor from this manufacturer. And as you see, the external quantum efficiency of the diode is quite greatly enhanced over a wide range of wavelengths, and also the operation regime on the wavelength range is enlarged. Also, the response uniformity from pixel to pixel throughout the whole sensor was improved by applying the nanostructures, black silicon there, and also the dark noise level of the sensor was improved by the black silicon technology. And these all, of course, greatly improves the signal-to-noise ratio of the camera, enabling higher quality pictures and also longer detection range. Another example from our development pipeline is extending the operational regime of our patented technology to longer wavelengths. And there we are developing so-called black germanium photodiodes, targeting mainly to the 1.2 to 1.8 micron range. We have some preliminary data available. The EQE of the black germanium photodiodes has shown to be more than 90% from 1.2 to 1.6 micron range, and also remain high for the whole or very wide range, which is outperforming any of the existing commercial germanium photodiodes, and actually it's also the quantum efficiency is exceeding even some indium gallium arsenide based detectors available today. A third and final example is this kind of quadrant detector that can be used, for instance, for some laser positioning applications. So the idea here is that the photosensitive area of the diode is divided in 4 quadrants, and then by reading the current from each of these quadrants, one can conclude the location of the laser spot on the diode. One example for this device is from the defense field. So this kind of device is put on the nose of the missile, and then the target is designated with the laser. And then this detector here is reading the reflected signal from the target and can then guide its path to the target. In this application, normally a wavelength of 1064 nanometers is used in the near-infrared range, and typically the photoresponse of these kind of devices and that wavelength is around 0.4 amperes per watt. With our technology, we have reached 0.7 amperes per watt on a bare chip, and with the packaged up to 0.65 amperes per watt, which is quite a big improvement for these specific applications. But of course, this also finds numerous other applications as well. In a summary, we at ELFys, we are disrupting the light sensing component market by providing photodiodes that have sensitivity that is higher than in any other photodiode product available on the market. This high performance, it's based on our patented nanotechnology, and the performance has already been proven in various different applications by our existing customers. And we have various different designs and packaging options available from the shelf as standard products, but we are also highly likely to customize the product for the customer needs. We are exhibiting here in this hall at booth 224, so please visit us. We have there a demo to show you the performance in live, and also some product samples that you can have a look. Please follow us also on LinkedIn to be among the first ones to hear about our latest news and the product launches. And I would also like to advertise our webinar that we will have in around 2 weeks, where my colleagues Mikko Juntunen and Juha Heinonen will discuss in more detail the technology and different use cases of our technology. With that, I would like to thank you for your attention, and the floor is open for questions if you have any. And of course, you are welcome to our booth to continue the discussion there.